Welcome to part 3 of our regression model plotting lecture. So in the previous tutorials, if you haven't looked at the previous tutorial, we were looking at plotting regression models, linear models mainly. In the forest plot, we were using several different packages, and we were plotting them in forest plots. In this particular video, I would like to focus more on logistic regression and putting the logistic regression models, mainly we will convert them, the beta estimates into odds ratios, and once we have the odds ratios, we will plot them in a forest plot. That's what we're gonna do today. So if you haven't watched my previous two parts of this model plotting lecture, I would advise you to look at these models so that you can have an idea of the data and our linear modeling and how we plot them in forest plots. To give you an idea of our data, let me show you how the head of our data, this is life expectancy data from 200 countries. So we have gone through some of the data wrangling steps. I just want to show you here how our data looks like. Because we were removing missing values and dealing with some distribution statistics, and let me just show you the head of this data set. So you see in this data we have the country, the year, and we have several different variables. And I think if we just have a look, the dimension, I think it's about 1,600 something. So we have 1,649 observations and 22 variables. So for today, what we're gonna do is we want to build a logistic regression model. So once we have the logistic regression model, we want to plot the odds ratios into forest plot, because forest plots they look nice, instead of putting your model output in a table. I mean, tables are also elegant. It's okay. It's even more informative with lots of details. But if you are giving a talk or presenting your results, figures might be worse than having tables. So the first thing we need to do is, because our dependent variable, let me have a look again, this life expectancy data. So our dependent variable is life expectancy. If you remember, for our previous modeling, we were using this life expectancy variable as a dependent variable, and then we were using some of the other variables into as independent variables. So we're gonna use, I think the first thing we need to do is we need to check the histogram, because this is numeric data. So what we want is we want to check the life expectancy information. So let me just have a quick look of the histogram of this variable. So I can simply take this and put it in the hist function, so I can have this kind of plotting. It looks like it's kind of normal distribution, but a little bit skewed to the left. So that means it's negatively skewed variable. So for that, probably we might have to look at some of the details of whether this data is actually normally distributed or not. So we can have a look, like a skewness, kurtosis, and the like. So maybe we can try the psych package. They have, I'm sure there are also other packages that are able to check normal distribution, but we can just try the psych package and have a look at some of the skewness and kurtosis and the like. So within the psych package, they have this this function called describe. So the describe package, the describe function will tell us the details of this variable distribution. So let me pass this. So life expectancy and ARM, and if I run it, it will give me some of these details. So I have the the mean and the standard deviation, the median, the trimmed, and I don't need the other ones. I just look at the this one, the skewness and kurtosis. So this is evidence of showing some sort of some sort of non-normal distribution. So this is a negatively skewed distribution. So my dependent variable is negatively skewed or skewed to the left. So for left negatively skewed distribution, usually it's recommended to do square root of transform you need to transform. If you have like if you have this kind of data, you may need to transform it. Let's say logarithm or cube root or square root. So if you have negatively skewed distribution, it's recommended to do a square root or cube root or logarithm transformation. With that, you can achieve normality. So to check, let's have a look. Let's say we can transform this variable into square root with the square root transformation, and we can have a look at the QQ plot. So to do that, let's have another package called ggpub_r, I think. And once we have that, we can see the QQ plot of this variable. So ggplot, ggqq, that's what we need. So ggqq plot. You can also do it with the base rqq plot qq plot function, but we can. So then I need to pass the square root, the transformed version of this variable, which means this one, life expectancy. So I will pass it with a square root of, and then pass it with a ggqq plot. Now I can run this, and probably I made a mistake here. So library, it's not library. So let me run this again. So now you see, it shows because this is a kind of nicer version of QQ plot. You can use ggplot. So this QQ plot shows the points fall outside the reference line. Some of the points, they are falling outside. This is a reference line. If all of these points are falling in this line, in this reference line, it's a QQ line. So if they fall along this line, then it's normally distributed. But in this case, they are falling outside of this line. So that means, we have we have a problem with our dependent variable. So maybe it might also be good to look at other tests. Let's say Shapiro-Wilk test. So you can check with the Shapiro-Wilk test maybe. Maybe if you know SPS in SPSS, it can also easily do it in SPSS, but in R it's much easier. So you just need to type Shapiro test, and you can pass this one, the square root of this variable. So you can simply pass this and copy this here, paste it here, and run it. So now it's showing some value, the W statistics, the wild statistics, I think, and the p-value of this match. So it's a small p-value. So with this, apparently, it tells me the p-value of Shapiro-Wilk test is rather much lower than 0.05, which means the null hypothesis, that is Shapiro data is normally distributed. So the null hypothesis for this is the data is normally distributed, but we are saying we found the p-value is much less than 0.05, which means we have to accept the null hypothesis. That means the data is not normally distributed. So therefore, I mean, as I said, if you in Shapiro test, the H0, I mean the null hypothesis, is the data is normally distributed, but because our p-value is much smaller than 0.05, that means we will have to reject the null hypothesis and conclude that the data is not normally distributed. So this is problem. So that means if you run a linear model using this variable, even with a square root of transformation, that means linearity assumption is violated. So that means you need to find other ways of modeling this data. So for now, what I want to do is I don't want to go to the details of this intuition. or further modeling strategies, what I'm gonna do is I will just change this life expectancy variable. It's non-normally distributed, so I will have to change it into kind of categorized into two categories. So for that, because it's the variable is non-normally distributed, so that means I will change it into two categories. So that means I will have to use median split. So if the value is above the median, so I will call it let's say high life expectancy, or if the value is less than the median, that means I will call it the observation has low life expectancy. So let me have a look, a summary of this, and I will take the median split. Just in case if this was normally distributed, you could have taken the mean. Actually, if the normally distributed, these values in the mean and the median would have been close to each other, or maybe nearly similar or identical in perfectly normally distributed condition. So now I will just use this median split. So to do that, what I'm doing is I will have to use this if-else function. So you see my mean. Actually, I don't need to transform it, because the transform it, whether you transform it or not, it's non-normally distributed. So I will have to use the non-transformed variable. I mean, it doesn't matter, it's the same, but you can still use also the non-transformed. Yeah. So now I have to use the median split. That means if an observation has, if x, let's say if x is an observation, or if an observation has a life expectancy of greater than this value. So if it is greater than this value, 71.7, that means it will be considered as high life expectancy. But if not, we will label it as low. So in the end, then using that categorical classification, we can do this thing called logistic regression. So let me write this. So then I would just use this if-else function. It's so easy. So you can write the life expectancy new. I'm adding a new variable, so it's called life expectancy cat, and then if-else life expectancy new. So this is my data actually. So this is what I want, and I will call this life expectancy. So if it is less than or equal to 71.8, that means I will label it as 0, which you can also consider it as high or low, or if it is more than that, it should be 1. That means high. But you can also label them, but it should also be possible like this. It's you can simply, you can use it. This is a bizarre way of doing it, but you can also use another like a dplyr or something to rename. Not to rename, like to classify. To rename the categorical labels. So let's say I'm doing this first. I categorize it, and the next one I'm giving 0 to low and 1 to be high. So in that case, you can just use factor. I'm also using factorizing it because it's a factor variable. Now I can simply do this. And okay, there seems something is wrong. Let me have a look. Okay, life expectancy cut, and okay, data has 1,600. Okay, I have a problem here, so I have to use this instead. So yeah, and here again it should be exactly the same data. I'm just adding a new variable. Now I can run it and it should work. So now if you want, you can also use a count function or table or something to check. Let me then count. It's changing my keyboard. So now I can count the life expectancy variable, this categorical variable, it should be low or high. Okay, life expectancy cut is not found. Why? Let me just do this. It should work. Oh, okay. I mean, there is also an easier way of doing it. You can just pass these here and maybe table, then and this, so you can have these values, low and high. So we have like kind of balanced classification. I mean, 842 have low life expectancy, and 807 has of the observation have high life expectancy. So now we already have our labels 0 and 1, so that means or high and low, they are also encoded. So that means you can easily run logistic regression. So if you want to logistic regression, we can use GLM. This GLM has a linear model. And then this is our dependent variable, which is classified into 1 and 2. And then okay, life expectancy cut, and then we can call all the other variables as a function of life expectancy, and then we define the family. So this is what you do. So total life expenditure, schooling, adult mortality, and so on and so forth. And finally, we define the data, and we define the family. The family is binomial, because we are doing binomial logistic regression. And then finally, it's simple, you can run it. Okay, so now it seems something is wrong. Life expectancy cut is not found. Let me call this again, and this data, so I'm probably placing this data here, so now it should work. Now if I look at the summary of this model, I should get the summary of this logistic regression model. If I run this, yeah, so now I have the logistic regression model, but it's data coefficients. That means we may have to convert them into odds ratios or those kind of things. So I'm not going to go to the details of all these AIC values. So that means, I mean, the AIC value is one of the key criteria that you can develop. You can build multiple models, and this is one of the comparison criteria. And depending on your AIC value, you choose the right model. I'm not going to the details of that discussion, because my goal is just to show you how to convert these coefficients, I mean these values, into odds ratios, and once you have odds ratios, you need to change them into you need to put them in a forest plot. That's what we need. Again, so for this, what we need is we need to extract the confidence intervals, and I think for that we can use the mass package. So the mass package, so you have you can require or library. I mean, require, if you are writing a package or a function, it's better to use the require, but if you are using it to simply, load the library, it's better to just use library. So let's extract the confidence interval, odds ratio confidence interval, and we will round it. And then what you need is the exponent function, the exponent, because you have to exponent all these estimates. And first you extract the coefficient of logistic regression, and then finally you extract the confidence intervals. If you look at our previous tutorial, I think you will find how we extracted this coefficient. Because this conf function, it will give you the coefficients. It will extract the coefficients of the model. And here I'm putting it into 3 significant digits, because it doesn't look nicer if it is more than that. Now logistic regression not found. maybe I have to check this. This is a model. Maybe I made an error here somewhere. So let me type it here again and again here. So now it should work, I suppose. Waiting for profiling to be done. Okay, maybe it's already done. Let's have a look how it looks like. Yeah, it's already done. So this is how the table looks like. So we just need to rename these variables. So what we need is we need to extract the variable names. Let's say odds ratio CI mutate variable name variable row names. We just need to because these are the variables, so I'm calling them as variable. I'm replacing them with that kind of name. Now the next thing is we need to convert. Maybe you have also seen in our previous tutorial. I also have shown how to rename these variables, like the lower bound, the upper bound, and the estimate. That means this is the odds ratio. If it is in our case, because we already exponented it, you have seen we exponented it, then it's not the estimate, then it's odds ratio. So for that, we can just simply use the rename function, and we concatenate all the coefficients. So you use the rename and then odds ratio, that is our data frame, this table, and then we concatenate v1 because v1 is here. It's adjusted odds ratio. We call it adjusted because it's adjusted by, it's a multi-variable logistic regression. So we have adjusted to it's not only one variable that's running that we run. We have adjusted for many other variables. So we call this adjusted odds ratio. And the 2.5%, this is with backticks because R doesn't like this space. So we have to put it in the backticks, and we call this lower bound and upper bound. Once we have that, we can run, and then we can also have a look at it again. Now, if you see, now our variable names are replaced, and the data frame looks more elegant and ready for plotting. Probably we need I don't know, one more thing. So let's reorder it. Reorder in a sense, the variable should appear on this side, and the other variables can go on that side. So that means we can just column order. That means the first variable is variable, and then adjusted odds ratio, lower bound and upper bound. Then you pass the data frame, and in this square bracket, because this is a column, so you, after the comma sign, everything you write here, it would be before the comma would be row, but after the comma is a column. That's how R works. So you need you need this. Now if I see this, the data should be look even better now. Variables rearranged. I'm sure there are many other ways of doing it, like reordering or something, but this is just the base R way of doing things without just using a package or something. So now we have the variable adjusted odds ratio, lower bound and upper bound, and from this we can simply run ggplot2. So with ggplot2, what we can is we can simply write this. Let me call plot, and let me remove this -1. That means intercept. I'm not plotting this, so I will remove this part, and because I don't want to plot the intercept in my forest plot. It might be, it's significant in the formula. It has, if you are looking, if you are working prediction model, so that in the formula, in the risk estimation formula, this intercept has something to do with, although the value is very low, 0.01, but it's still significant. No, not really significant. So it's not significant. So in this case, you can drop it because it's it's passing. No, it's actually significant. So it's from 0.0 to 0.03. Anything that touches 1, any odds ratio that pass through 1 confidence interval, then that means it's not significant. But in this case, it's from 0 to 0.3, so it should be significant, I would say. You can also see from the previous model, so the intercept is significant. Yeah. Okay. Let me add the other. So that means let me call this plot logit model and odds ratio confidence interval. I'm removing the intercept because I just didn't want to plot it. But as I said, if you are dealing with some risk estimation or risk prediction model or something, then you would have to add the intercept in your formula, in your risk estimation calculation. Now, the next thing what I do is I need to use this ggplot function, and the aesthetic mapping, that means x would be, let me reorder the variable by their adjusted odds ratio value, and the y would be equals the adjusted odds ratio. Then what I can is I can add G on point. This is what I need. So G on point, and within G on point I can do some changes. Let me make the shape 15. So that means it will be like a square sign in the plot. The size should be 4. Let me make it 4, and the width would be about 0.1. But that's just a matter of trying different values and finding the right plotting. And the position has dodge, and let me make the color gray. Color equals let me make it black. Okay, black. And then plus let me add, if you run this, I think we will see, so if we plot this, and we'll see the points now. We won't see the error bars or the confidence interval, but we'll simply see the points. Let me, if you change this to 19, I think it should be like diamond. I'm not exactly sure how this, but there are about 20 something shape. So this is like a circle. So that's this is where you control the shape of this. Yeah, but let me put it as a square sign, so then it will look like this. Maybe I can ignore this dodge and see what it looks like actually. And yeah, okay. It also doesn't like the width since it's duplicated. I don't know, maybe. And yeah, it's working. So that we can ignore the other arguments. So now we can add is the geom error bar, error bar, and then we can add within the error bar we can do the aesthetic mapping. The x equals y min. No, not x, y min equals what was this? Lower bound. I think we called it lower bound, and the y max should be upper bound. The y max equals upper bound. Now, if we just simply run this, it should appear the plot. I mean, the confidence interval should appear like this. So now the next thing we need to do is just we need to flip it. So we can flip this. So to do that, because it's there's they are appearing the variables on the x-axis and the odds thresholds on the y-axis, but then when we flip it, the plotting looks a little bit better. So for that we can use chord flip. So we can simply flip it, and now it should look better. Now it's flipped. We just need to change this, how it looks like. But I think that one can be changed with width and size. So let me try that. Somewhere here, and width equals okay, should be, so it should be outside the aesthetic mapping. So the width is 0.2 and the size equals 0.7. Let's try this and then run again. So now it looks better, but you can also color, you can change the color. Maybe if it looks nice, green for example. I like green color, but green could also be, for some people, it may not be readable. Let me keep it as it is and change the color of the error bar. So I can simply change it into color equals dark green, for example, dark green. Now you can run this. I've made it a comment. Yeah, now it looks like this. It's a little bit better, but you can, and then what we can add is the V line, the vertical line, this V line, like this thing called geom-h line. So for that, we can add geom-h line, and we define the y and the x intercept. We can also add it here. It's fine. So geom-h line, y-intercept 1, color is red, and we made it as fat as just 1. Just the size should be not bigger than this one. Yeah, so that's how it looks like. But if you would like to change some of the plotting options, you may have to look at the themes and like element text things, the theme. With that, you can manipulate the x and the y variable levels and how they should appear, how big, whether you need them in bold or things like that. But the whole thing, this whole what we have done until now, it can be changed, can be plotted easily using this sjplot package. So if for those of you who don't know, you can just simply load sj plot. P is capital, so you see sj, and P is capital. So you need to, if you don't have it, you can install, and then this is a ggplot way of long way of doing it, but the easiest would be using this Sringyaka has already written a package for us. So what we just need is plot model function of the sjplot package, and then you can simply add the logistic regression model. So once you have that, you can run this, and it looks like this. So what you're gonna do, what you want to add additional arguments. So now let me add show values. That means the odds ratios will appear. So if I assign, by default it's false, but if you make it true, then you will have the labels. And let's say if you want to add the vertical line color, that means the V line color, it's white, there is a white thick line here, but you can also change it into red. Usually I would use red, because that's the null point where the models are non-significant. Where the values are the non-significant regions, it's the null point. I always prefer to use a red color, but depending on your choice and how do you want to present it. I advise to look at the details of plot model function. Yeah, so you can simply, as always, you can write help or question mark sign, and then simply run. Then you will have all the arguments for plot model. Additionally, if you would like to check more models, like for mixed models, for any other models, it's also possible to do this sjplot. They have many different this plot model works for many different kinds of models, but I just show you how it works with the linear model and logistic regression model. But you can also try it for additional, for the other models. As long as you have risk ratio and odds ratio or beta coefficient outputs from your logistic regression models, then you can use this package. The last thing probably I would need to use evaluation of logistic regression model, evaluation of model performance. So I would probably make one last lecture about, last presentation about this. How do you evaluate them? Usually people prefer to, I think the old way of evaluating models is just using Hausner-Lumschow test and the like. But that's not really the right way of evaluating models. That's So what you do is usually you use your model for predicting the values, predicting the observations. The gold standard way of evaluating your model is like you classify your data set, you train a regression model or logistic regression model, and then once you train your logistic regression model, you use that model to predict the data, to predict the test data set, because you need to split the data into train and test, and then based on the training data set, you train your model using your training data set, and then once your model is trained, you can use it for prediction. And then once you have the prediction, you can check the prediction accuracy. Let's say in logistic regression, if your data is balanced, you can use accuracy. But if your data is not balanced in a sense, the classes, the dependent variable values, the categories, if they are like balanced, like 50%, or 49, 50 something, for 51, then they are balanced, so you can use accuracy. Otherwise, you need to use other values like area under the curve value, or maybe sensitivity, specificity values. For linear regression model, you use a different loss function that is root mean square error or mean absolute error and the like. So that's the way you can evaluate model performance. You can compare models. You can you can see the mean absolute error, root mean square error for linear regression model or for regression problems. But if you have a classification problem, that means if you have to classify the observation into two categories or two or more categories, then you would have to use a different way of evaluating performance. That's how you do it. Maybe in the next session I will start doing some talks or some YouTube tutorials about this issue. Until then, enjoy data science in R and in Python, and I would be very happy if you can subscribe to this channel and follow what is happening. Thank you. Keep in touch.